Hi, my name is Eugene Kwan, and in this video, I want to make some sense out of glycolysis. And I want to teach you how to understand glycolysis without memorizing a ton of seemingly random structures. So, if you look up glycolysis in any textbook, I just took this from Wikipedia, you see a really complicated diagram. And when I was first learning this, it really felt like trying to memorize a subway map in a city I'd never been to in some other language. And worse, I think the subway map looks totally random. We know we start from glucose, that's supposed to be the fuel in glycolysis. But then for some reason, we're phosphorylating at these various positions and then randomly converting glucose to fructose. It just doesn't seem to make any sense. Right? If the whole point of glycolysis is to make ATP, why don't we just phosphorylate ADP, right? Why do we need glucose? Um, Now, if you know a little bit more about glycolysis, you might know that it also involves NAD+, and that's actually used as an oxidant. But why do we need an oxidant in this reaction, and how does that help us make ATP? And then there's also kind of a peculiar feature to this pathway where we're phosphorylating in these various places, but we're not really activating any groups as leaving groups, right? Often you'll activate an alcohol as a phosphate, um, to make it leave, but we're not doing that, right? Even though a lot of textbooks call this sort of an investment phase and a payoff phase. It's not like we're activating an alcohol as a phosphate and then making it leave, and that's generating ATP. You'll see that's actually really counterproductive in this pathway. Okay, so I think a better way to think about glycolysis is that it's three coupled reactions. So the actual glycolysis part, if you think about the word glycolysis, means basically just to split or chop up glucose, right? And glucose is a six carbon sugar, and we're chopping into these two identical three carbon pyruvate pieces. So that's the chop part of glycolysis. And in the process, we're actually also going to use up two equivalents of NAD plus. That's our oxidant. So glycolysis is also an oxidation, and that oxidation is going to release energy. And we want to capture that energy in the form of ATP. Okay, so why oxidation? Um, and it's just a fundamental fact of the universe that oxidation of carbon is going to be exothermic. So here's an example of the oxidation of an aldehyde with oxygen. And when we uh, split oxygen, which is sort of a relatively weak bond, and attach those oxygen atoms to carbons, we actually form much stronger bonds, and that's why energy is released. So how can we tell if a carbon is being oxidized? Okay, so the quick and dirty way is really just to count the number of carbon-oxygen bonds. You can see here that in the aldehyde, you've got two carbon-oxygen bonds, and then in the acid, you have three carbon-oxygen bonds. So in that very crude sense, we've increased the number of bonds. That's an oxidation. But the more precise way is to look at the oxidation state of that carbon. Okay, so for example, we want the oxidation state at this spot. We're just going to dissociate all of the bonds ionically. Okay, so if we look at the CC bond, we know bonds have two electrons in them, and carbon has, of course, the same electronegativity as carbon. So we're just going to split those electrons equally, giving one to this atom and one to this atom. So now we have the central atom having one electron. Um, Now we can do the same thing with the CH bond. This time the carbon is more electronegative than the hydrogen, so under this ionic rule, we're just going to give both electrons to the central carbon, now having three total. Um, and in this carbon-oxygen double bond, well, the oxygen is more electronegative. It gets all the electrons. The central one gets none. And so in the end, we have four protons on this carbon and three electrons, giving an overall oxidation state of +1. And I'll leave you to do the same thing for the carboxylic acid, but you will see that the oxidation state is now +3. And so this is a two electron oxidation. But if you don't want to do all the counting, you can just note that there's an increased number of carbon-oxygen bonds, and that's an exothermic process. Now, this particular example was going from an aldehyde to an acid, but really you should think of uh, carbon on this sort of redox ladder, right? So all life on Earth, or most life on Earth, lives in this oxygen-rich atmosphere. And if you define the redox potential relative to oxidation, you get this ladder, where really reduced carbon is very high in potential energy, and as you successively oxidize it, you release quite a bit of energy. Uh, and so, if we go backwards, the opposite of the process is hydrogenation, right? So this is a two electron, two proton reduction. You can think of NADH as having a hydride in it. So that's the proton and the two electrons, and then the other part of the hydrogen is a proton. Running it backwards, we have an oxidation, right? This is what's happening in glycolysis. We're oxidizing some piece that we cut out of glucose, eventually to pyruvate. And overall, we'll find that we use two equivalents of NAD+. So this will be a overall four electron, four proton oxidation. And I'll leave you to verify the oxidation states here. So here's how I want you to think about it in terms of the big picture, right? So often people say, glycolysis is to make ATP, or we want to cut glucose into pyruvate. I think those things are distractions. You should really think of it as an energy harvesting machine, just like a dam is, right? So in a hydroelectric dam, you take water, which is at a high gravitational energy, and you let it flow uh, and have low potential energy, right? And then you try to harvest that kinetic energy as electrical potential, right? So the flowing water spins a turbine, and that increases the potential energy of some electrons that can then be used to do work. Um, what you're not doing with the dam is making water, right? That doesn't make sense. It's just water is flowing around. And it's the same with the electrons. You're not making electrons either. You're just taking high potential water and turning it into high potential electrons, right? So in glycolysis, it's really the same thing. We're taking the high potential energy in glucose and turning that redox potential energy into chemical potential energy in ATP. And to let that flow happen, we're going to use NAD plus as an oxygen surrogate. Okay, so think of glycolysis as an exothermic oxidation where we're going to capture the chemical energy in ATP, right? So there's a chopping, right? We're going to chop glucose into two pyruvate pieces, and part of the energy is going to come from oxidation, which is exothermic, and part of it is going to be coming from the fact that making double bonds is favorable. And actually, you're going from one molecule to two, and so there's actually an entropic component as well. But in any case, you're releasing this energy that you're going to then capture as ATP. Okay, so the question then is, how do we chop up glucose? Um, right, what is the kinetic pathway to release the thermodynamic energy in glucose? So if we sort of dramatically simplify the structure of glucose, just forget all the stereochemistry and all these hydroxyl groups. If you just think about glucose fundamentally, it's a five carbon ring with one carbon outside the ring. And if you just chop that ring, no matter what chemistry you use to chop that ring, you're going to end up with two unsymmetrical pieces. And that's going to be annoying biologically, right? It's going to be expensive because now you're going to have two whole sets of completely different machinery to process both halves. It'd be way nicer if you could chop glucose into symmetric pieces that then can be processed with the same machinery. Okay, and so that's the point of making fructose. If you look at the structure of fructose, fructose is a five-membered ring, but four of them are carbons. So that means if you chop it, you can see the structure is quite symmetrical, right? You've got the two carbons on each side, so that's why it's 1 plus 4 plus 1. You have an even number of carbons in the ring, so if you were able to chop it along the line I've indicated here, then you would end up with some symmetric pieces that you can process with the same machinery. Okay, so in terms of arrows, what do? So you take the hemiacetal and then you make the open chain form of fructose. And if you look at this, you'll see that there's a beta hydroxy ketone in it. And that's the retron or pattern for an aldol reaction. So if we run the aldol reaction in reverse, if we do a retro aldol reaction, we're going to fragment this molecule into glyceraldehyde and this very interesting looking enediol molecule. And if you look at this enediol molecule, you'll see that it can tautomerize. Now, it can tautomerize one of two ways, right? So if we protonate at this carbon, then we're going to end up with dihydroxyacetone phosphate. And that's kind of what we don't want because we've already made glyceraldehyde in the other piece here, right? And so nature's come up with this very clever solution. It says, I'm just going to let that tautomerization be unselective, but I'm going to provide an enzyme that lets these things equilibrate, right? Because if we protonate at this other uh, carbon, then we're going to end up with the desired glyceraldehyde phosphate. So let's just provide an enzyme that's going to isomerize these. And then I'm only going to provide enzymes to process glyceraldehyde 3-phosphate. And so even though it turns out that this glyceraldehyde is slightly less stable than this dihydroxyacetone, it doesn't matter because equilibrium will just drive the reaction this way, and all the undesired dihydroxyacetone phosphate will go away, right? And that's what we call the Curtin-Hammett principle. Your energies of the sort of starting materials here don't really matter. It just matters which one is more reactive. And so now we can just process glyceraldehyde with one set of enzymes and not two. Okay, so how do we get from glyceraldehyde to pyruvate, right? We know that's where we need to end up. So can we just draw some sort of naive arrows that will get us there? Okay, well, of course, we already talked about the fact that we have to oxidize glyceraldehyde um, to this glycerate, and you can do that with NAD+. Okay, so let's just imagine you do that. And then you know that protons, alpha to carbonyls are acidic, right? So we can do an E1CB reaction, right? If we deprotonate here, we'll generate this anion. Beta to this anion is a phosphate leaving group, right? And note that it's a low energy phosphate. And we're going to form this enol, and this is actually the enol for pyruvate, which is great, right? We made pyruvate. But the trouble is that we didn't actually make any ATP. Instead, we've lost this phosphate, and we haven't captured any potential energy. Uh, so, if you remember where the phosphate came from, this phosphate came from the hydrolysis of ATP, right? So this is sort of a losing proposition, right? So what we need to do is somehow couple this oxidation process to ATP synthesis. Okay, and that's what we call oxidative phosphorylation. All right, so what is that? The normal way, I think, that's easier to think about ATP is that it's a way to drive unfavorable reactions forward, right? So ATP hydrolysis is favorable. So if you want to do something like amidate glutamate to glutamine, which is unfavorable, you can kind of pay for this desired process with this favorable ATP hydrolysis process. Okay, so now if instead of wanting to make an unfavorable chemical reaction happen, we actually want to make ATP from ADP, we just have to run this whole thing in reverse. Okay, so what we can do is we can couple a favorable reaction now, which is, of course, the oxidation of the aldehyde, to the unfavorable synthesis of ATP from ADP. Okay, and that's what we call oxidative phosphorylation. And I think that can be confusing because it sounds like the phosphorylation is oxidative. And no, phosphorylation is redox neutral. What we're saying is that oxidation is actually driving phosphorylation, right? And so there's some kind of coupling between these two things. And what you'll see is there's not actually a good chemical mechanism to directly couple these processes. So the coupling will actually be indirect. And so here's how it works. In the glyceraldehyde phosphate case, you oxidize the aldehyde with a dehydrogenase that uses NAD+, but in the same enzyme, you'll simultaneously capture the carboxylic acid that you generate with phosphate. Okay, and so this is going to generate this high energy mixed anhydride. I've indicated the high energy phosphate in red here to distinguish it from these other low energy phosphates. Um, and so in the first step, we oxidize and we make this high energy phosphate. And then we're going to transfer this high energy phosphate to ADP in another step. All right. So in the second step, we use this as the phosphorylating agent for ADP. And then now we have our universal ATP currency. Okay. So now we've paid ourselves back, right? Essentially, we put in one ATP per half, and now we've gotten back one ATP, which is good. But now we still have to get to pyruvate. And if you remember what we just said, you could try to do E1CB directly on this, right? Generate the anion here, but then we would lose this terminal phosphate again, and that's bad news, right? Because then we'd get to the end and we wouldn't capture any energy. And so what you need to do is actually move the phosphate. So you can just have an enzyme move the phosphate from here to here. That's roughly thermoneutral. And then you do E1CB on that. Okay, so now you have to lose hydroxide, which we normally say is bad, but you can catalyze that with a magnesium ion, right? And it will turn out to be worth it because once we eliminate hydroxide, we're going to generate this high energy enol phosphate. And this high energy enol phosphate can then be used to phosphorylate ADP. And now we've captured our second ATP, and now we're in the black for this reaction. So um, now we're at pyruvate, and that's the end of the pathway. Now, I just want you to note a couple features here. So previously, when we oxidized this glyceraldehyde, we had to put a phosphate on at the same time as oxidation. In this case, the phosphate that turns into a high energy phosphate, see it's blue here and then red here, was already on the substrate, right? So it's not a requirement that you're adding phosphate. So oxidative phosphorylation may not actually involve phosphorylation in that first step. And the other observation I'll make is that the energy here is not actually coming from oxidation, right? So before we oxidize glyceraldehyde to make this acid, that's oxidative and that's exothermic, and we captured that. But now what we've essentially done is to take two carbons, oxygen single bonds and put them together, right? You might have wondered, like, why does pyruvate have this funny structure where both carbonyls are together like this? And it's just because having a carbon-oxygen double bond turns out to be more favorable than having two carbon-oxygen single bonds. Okay, so now we can zoom back out, but with a little bit more detail. Okay, so what we're doing in glucose is we do some symmetrization first to make this fructose 1,6 bisphosphate, and this nearly symmetric intermediate, when chopped, will give us glyceraldehyde 3-phosphate through that ene diol, right? And having a common intermediate is going to let us save a lot of unnecessary enzymatic machinery. Okay, and then we're going to couple indirectly oxidation, which is exothermic, to the phosphorylation of ADP, which is unfavorable, and that's going to result in a net payoff of 2 ATP. Okay, and overall, the energy from this is going to come both from oxidation of an aldehyde to an acid and the moving around of bonds to a more favorable arrangement. Now you'll note that in this process, we're using up NAD plus, and then that's going to generate NADH. And if you want glycolysis to keep going, then you're going to need to have some way to turn NADH back into NAD plus. Now, if you have oxygen, that's a straightforward proposition. You just oxidize NADH. But if you are under anaerobic conditions, then you just sort of kick the can down the road. So you can just take NADH and then reduce pyruvate to lactate, and then you can either deal with it later or you can send it elsewhere, right? And this is actually something that's very important in sports medicine. You can, as you get more fit from running or whatever, then you get very good at transporting lactate out of cells and sending it to the heart, which is much better perfused. So you can oxidize NADH back to NAD plus there, right? So you can kind of be anaerobic peripherally, but then aerobic in your heart. Okay, so just to conclude, I'm going to go through this. This is the sort of full subway map, but hopefully this time you can see that there's a beautiful logic to how it works. Glycolysis is actually this really, really old um, energy harvesting machine that's been around, we think, for maybe 4 billion years, right? It's just in all the oldest DNA we can find. So, almost every organism on this planet uses glycolysis to extract energy, right? You can think of the whole business of life as sort of trying to get energy out of the carbon redox gradient that's created by having an aerobic atmosphere. So I think that's really deep and amazing. So I'm just going to go through this pathway uh, and just try to point out some of the features that we noticed along the way today. Okay, so we're starting from glucose. Remember, we have this 1+5 nomenclature indicating that it's a five-membered ring with one carbon outside. Five is an odd number. If you try to chop that, you'll get unsymmetrical pieces. So we're going to try to make symmetric pieces that we can process with a common set of enzymatic machinery. Okay, so we're gonna use a series of phosphorylations to end up at fructose 1,6 bisphosphate. And now you see it's obvious why you need to phosphorylate twice, right? If you only phosphorylate once, this will be unsymmetric. Now, of course, there are other reasons to phosphorylate. You're going to keep things in the cell. You can regulate things. It's a handle for enzymes to catalyze stuff. But I think fundamentally, just for understanding the pathway, you should just think of it as trying to get to the most symmetric intermediate. All right, so then we're going to open up this hemiacetal, and then we're going to do retroaldol to chop it into glyceraldehyde phosphate and dihydroxyacetone phosphate. And these are going to be related by an enediol intermediate that and this tautomerization process is going to be catalyzed by triose phosphate isomerase, which is an amazing, what they call perfect enzyme that essentially works at diffusion controlled rates. Right? You can imagine there's a tremendous amount of evolutionary pressure to make glycolysis very efficient. And so this enzyme has been extensively studied, and basically everything in that enzyme works really, really well, so that as soon as you get any dihydroxyacetone phosphate, you can actually funnel it over into glyceraldehyde, and you can think of metabolic flux as always pouring stuff out of this side. Okay, so this is not a dead end anymore. And that's the curtain hamlet that we were talking about. This is slightly less stable, but much more reactive, and that's going to go into this downstream branch of the glycolysis pathway. All right, so now we're going to oxidize, giving us some energy, right? We're going to oxidize this aldehyde to an acid, and in the same dehydrogenase enzyme, we're going to phosphorylate that acid to generate this mixed anhydride. That's a high energy phosphate that can then be used to phosphorylate ADP. And so now we've broken even, right? So for one half, we put one phosphate on, now we got one out. And now we need to get to pyruvate. And as I said, you don't want to do E1CB. The phosphates are not there to be good leaving groups. Because if you do that, then you're going to generate sort of low energy inorganic phosphate, and that you've just lost the energy. You're not harvesting anything. Okay, so you take the 3-phosphoglycerate and you need to move the phosphate to the 2 position, and then you're going to do E1CB from this. So deprotonate here, lose hydroxide, and now that converts this phosphate, which was already here, into a high energy phosphate. This You can see this enol pyruvate looks a lot like just an enol if you replace P with H. And so essentially what we're going to do is use this enol phosphate to, again, phosphorylate ADP. That's going to generate our second equivalent of ATP and simultaneously essentially tautomerize this to the final product, pyruvate. And of course, in this reaction, we've had to use two equivalents of NAD plus, and the product is NADH. And if you want to keep doing glycolysis, then you need to either oxidize NADH under aerobic conditions, or if you don't have any oxygen around, you can kick the can down the road. You can use NADH to reduce pyruvate to lactate, and that will either just build up until you can deal with it, or you can send it somewhere else. Okay, so I hope this video has really clarified glycolysis for you, and I would love to hear your thoughts in the comment section. Thank you.